All right, recording is rolling. It is Tuesday, September 3rd. Welcome back from Labor Day weekend. Hope you guys had a good weekend. Agenda, a bunch of you guys just turned in these linear motion puzzles, so thank you for doing that. I'll be grading these tonight. Got some graphs on the back. I got those. So I'll be grading those. Okay, so I have the starter question here. We're throwing the ball upward. We're gonna take a look at that. You guys have your laptops out because in a few minutes we're going to do Kahoot. Actually, I do have the pin ready to go. The pin is on the whiteboard right here. Right, so yeah, in a few minutes we'll be doing that. Okay. At the end of class today, I'm gonna get you guys your first take-home quiz. Take-home quiz. All right, let's do it like this. I'll hand this to you guys right at the end of class. Right at the end of class, pick up that. This is going to be due on Friday. Did you guys write that in your planner? Write that in your planner. Take-home quiz is due on Friday. So of course we've been doing linear motion for a while, just motion in one dimension. We've got like throwing balls up or falling down, or maybe sometimes you're in a car speeding up or braking to a stop. Those are the main scenarios that we're looking at. Right? It could be a constant velocity situation like that. Tomorrow I want to get going on projectiles, which is going to be more like, what if you're up on top of a cliff and instead of dropping a ball off the edge of a cliff, like like I had right here, like dropping the ball. What if instead you throw the ball to the side? It goes way out. Like, can you figure out like how far does the ball go? Could be one question, things like that. Got some labs signed up. Okay, so that'll be tomorrow. Oh, here's what I want to say too: is projectile motion has no new formulas, so it's the same equations we've been using all along. You guys remember these three kinematic formulas, right? So it's the same ones. There's no new content in terms of formulas. Okay? But we're just going to be starting to think in 2 dimensions tomorrow. Just want to plant that idea, get you guys ready for that. All right, so let's take a look at the starter question. So down here, maybe ground level, I'm going to throw a ball straight upward. And I can throw it 30 meters per second. For American context, that's about 67 miles an hour. But you don't need to know that. That's right. So I'm throwing up at 30 meters per second. How high does the ball go? Right. All right. So we are a few minutes into class. I want to give you guys a little time before I hit record. Does anybody have the answer by now? Does anybody know? Not quite yet. All right. So here, so we'll start walking through this then. You guys know you're probably going to be using one of these, probably, right? Maybe something off this page can help you out. Okay. And there are how many different variables floating around? There are 5, right? There's time, acceleration, displacement, initial velocity, final velocity. Okay. And how many of those 5 do you need to identify before you can even solve something? 3. Okay. Right. What about to the starter question? So let's take a look at the starter question. Here, let's get this agenda off the board. Just full focus on the starter question. Oops. Get rid of about this. All right, that's the solution going on there. You guys don't know that yet. Okay. All right, so you said you need to be able to identify 3 different variables. How much do you know right now? Okay. Well, for sure, you know initial velocity could be 30 meters per second. Okay, that's the only number that I explicitly gave you. Can you think of anything else you might know? Gravitational pull. Yeah, because what if this was on the Earth versus the Moon? Because if you threw a ball up 30 meters per second on the Moon, do you think it would go a lot higher than on Earth? It sure would, because there's less gravitational pull. So you would have to know the gravitational field. A lot of times in physics, this is an implied value. Do you guys think it's implied that we're on Earth? Implied that we're on Earth? So gravitational field is equal to what number again? Yeah, 10 meters per second squared. Also, here's another detail. If we're talking about vector values, the direction matters. If I throw upwards and gravity's pulling downwards, do you think at some point when I set up an equation, there's going to be a negative sign somewhere in the mix? Something's positive, something's negative. Because I'm throwing upward, gravity's pulling downward, that's opposite directions, right? But there's still got to be something else you know. Otherwise, you can't solve it with just that. What else could you possibly know? How about this? You're going from down here to up here. Is that true? Right. Right. So I know how fast it's moving down here. Hey, who knows how fast it's moving up here? At the very top. 0 meters per second. Isn't that true? Is it true? If you throw a ball straight up at its maximum height point, it's going 0 meters per second just for 1 instant. And that would give us 3 kinematic values, wouldn't it? Boom, 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 just like that. Oh yeah, so you guys taking some notes. You guys write that in your notes. Be helpful. All right, guys good? All right. So here's what we know. We know the velocity at the beginning of the interval, that's to say at the bottom. We know the velocity at the end of the interval, that's to say at the top. And we know the acceleration because there's a gravity field. So now what? Right. Let's run to these formulas. Right. So you know the two velocities, you know the gravitational field, and I'm asking you for the height change. Does that look like a job for the first, second, or third kinematic formula? The third, you're saying? The third? Right. All right. You know what? I like that too. Yeah, let's do that. Let's do it. Let's do the third one. Third one. So we're gonna set up this form. Well, first okay, that's what we're looking for. H max. Right. First, I'll just pull it straight off the poster. Just copy paste it right there. Right. Now I can modify this a little bit to match this scenario. Like, instead of some general acceleration, could I call that a gravity field? And instead of some general displacement, could I call that a height change? Right? And it's going to look like this. So I usually try to solve it like this, where I split my paper, and on one side I'll solve in terms of variables, and the other side I'll go ahead and plug the numbers in first. You don't have to do it both ways if you're like solving it for a quiz or something. You can just pick your favorite method. But if you solve it in terms of variables, that could have some advantages. If you're solving a bunch of problems, suppose you got a bunch of friends and they're all throwing at different speeds, you could get a general answer that's going to answer a problem. Right? But whether you plug in numbers first or not, it's going to look something like this. So now final velocity will let go to 0 meters per second either way, because that would mark the maximum height point. Right? I'm throwing it some initial velocity. It's like right there. Gravity's pulling down at 10 meters per second squared. Oh, look, I pulled a negative sign out. You see, I went ahead and put in the negative sign. So I'm throwing upward, gravity's pulling downward. Okay. And then I'm solving for a maximum height, which is going to be a positive value because it's going upward. Looks like I'm defining up as positive and down as negative, I think. Right? And that's what we're solving for. Okay. Right. You guys good so far? All right. What's the next algebraic step? Can I take this 2GH and add it over? Maybe something like that, you guys think? Could look like that, right? Sure. Oh, yeah, the 30 squared could be 900 if you're doing the numbers. All right, is that all good? Okay, and then the very last step, could you divide the 2 and the G down? Okay. It'd be bam, just like that. There you go. So the answer is 45 meters. If you can throw a ball straight upward at 30 meters per second, it's going to rise to a height of 45 meters. And then, of course, it'll fall back down. On the left side of the paper, I got the answer in terms of variables. So let me show you that this does work out. So I'm making the claim maximum height is throwing speed squared divided by, and then in parentheses, 2 times g. Okay. Hey, it's 45 meters. Look at that, 45 meters. Same thing. Right? And again, in terms of variables, so you could bring in, let's say Bob has a friend, Alan, and Alan can throw, let's say 40 meters per second. Ooh, look, the ball's going to go higher or something like that. Right? How about this? How about this? Guys, what if Alan can throw twice as fast as Bob? That's going to be how many times as high? What's a factor of 2 squared? 4 times? 4 times? Right. Let me try that, because I know Bob could, we're back to Bob. Bob could throw at 30 meters per second. So Bob went to 45 meters high. Right. Let's bring in Alan. Alan can throw 60 meters per second, which is double the speed. Should be 4 times as high. Hey, that is 4 times as high. 45 and 45 is 90, and 90 is 180. That is, right? That's another advantage of solving in terms of variables, is you can scale things, even for proportions like that. Right, guys good? Right. Oh, see, last class, students wanted to solve this a little bit different way. They said, hey, could you use the second one, solve for time, take the time, plug it up in here, and solve it that way? And see, dig through my notes. Yeah, we did that too. Here's the other way to solve it. Okay, I can use the second kinematic formula to solve for time. I'm gonna get 3 seconds. It takes 3 seconds to go to the peak. And then once you got that, go to the first kinematic formula, plug in 3 seconds, and all the other numbers. If you're that fast, gravity's pulling down that much, you still get 45 meters. Okay? So different way to go about it. Okay. Hey, oh, you know what? I've got another way to look at it too. You guys remember drop a ball off a cliff? Okay. So For the ball to pick up to 30 meters per second, maybe this is like a backwards version of this, or maybe it's the ball falling down version. If a ball's been falling and picks up to 30 meters per second, how far did it fall? Turns out 45 meters. Ooh, and it's been falling also for 3 seconds. Look at that. It's pretty much this row right here is the falling down version of that question. Right? And here's frame for frame to draw it. Guys, this diagram right here is going to be really helpful later. Right? So what if Bob throws the ball straight up at 30 meters per second, and I take a picture every second? You see how at first the ball was thrown up the big distance, and then it gets less far, less far, less far. And here's the maximum height point, and the ball starts falling down, and then it goes further, 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 like spreads out. Okay. So let's look at different physical values, like velocity. I threw it up at 30 meters per second. Guys, after 1 second, moving straight up. Now how fast is it moving? See, it lost 10 meters per second every second. Now it's down to 20. Another second, now it's down to 10. Another second, now it's down to 0. That's the maximum height point. And then it falls down, picks up 10, 20, 30 meters per second. Is that great? Now that's all the black ink. I also have some pink ink up here. The pink ink is acceleration. Right? As soon as the ball leaves your hand, is it under the influence of only gravity? And gravity only pulls at how much? On Earth, 10 meters per second squared down. Right? Is that true? And so that's true all over the place. You guys get pink ink? Is that? Right? There's a bunch of different perspectives, and it's all reinforcing each other. Is that true? Right. This is not going to be the last time you see this. I'm going to pull this up later too. Right? You guys good? All right. I got another starter question for you guys. You guys ready for another starter question? It's going to go like this. Boom. Suppose Bob can throw. Oh, that's where I got Bob from. Sorry, there's Bob. Right. Bob, this same guy, can throw a ball, and it can go 45 meters high. Right? Hey, maybe this is a more practical version of this. Let's say we get Bob and his friends. And there's Alan and Bob and Carl and Derek and Eric. And they're all standing by this like multi-story building. Let's say, hey, you can throw the ball the highest height. Right, so I'll throw the ball the highest height. Or I'll say, I can throw up to the 4th-story window. I can throw up to the 5th-story window. Okay, how many meters from each floor? Okay. And Bob figures he can throw it up about 45 meters. So, okay, I think it's going up about 45 meters. Okay. And then they break out the question, well, if we see how high it's going, hey, I wonder if we can back calculate how fast we were throwing it to begin with. You guys see this is the exact reverse question, isn't it? Okay. By the way, what is the answer to that question? 30 meters per second, because I'm just starting with the answer to the last question, right? If you can throw it 30 meters per second, it must go 45 meters tall. Therefore, if you throw it 45 meters tall, must be that you can throw it 30 meters per second. But let me back that up with the math, because I wonder what the solution actually looks like. So here's what you would be given is the displacement, the height in this case is 45 meters. I know gravity's pulling down at 10 meters per second squared. So again, one's up, one's down. Maybe I need to tag a negative number to one of these numbers, right? And at the very top, it's going 0 meters per second because that would correspond to maximum height, right? Just like before. Right? This is going to play a little different. See, I'm trying to solve for what is the throwing velocity, right? And I'm going to use the same formula because notice I did not say how much time it took to reach the top, and I didn't ask for that, although it did show you a minute ago, 3 seconds up and 3 seconds down, right? But they didn't ask for that, so maybe this is the fast way to solve this, right? They show 2 different ways. If I split the paper, on the left side, I've got it in terms of variables. Right? Instead of 2ax, I called it 2 and g and h, and then I'm going to throw in a negative sign because gravity's pulling down. Right? On the right side, I went ahead and plugged in the numbers first, which a lot of students prefer to do, so that's okay too. You plug in the numbers first, you'll still get the right answer. Right? So I got the general solution of variables. I got the numbers plugged in. Could you guys do some algebra? Maybe take the 2gh and add that over to the other side. Could look like that. Right? You guys, what's the very last algebra step? Do what to both sides? Square root. Yeah. Right. Oh, and look at that. Square root of 900 is 30, and then the units follow, and it's meters per second. Right? Which is exactly what you guys said it was going to be. Is that true? Okay. And this another reason I want you guys to see this is in terms of variables. Now that's an interesting expression. I see the throwing speed would be square root 2gh. This is not going to be the last time you'll see this expression, square root 2gh for the speed. You'll see that all over the place. Suppose you drop a ball off a cliff. Or actually, I got dropped a ball off a cliff here. Is that really true? That if you know the height change, like from this right column, you get the speed by doing square root 2gh. Let's see. Let's try it out for, how about this one right here? All right, so square root 2 by 10 by, let's do a 45-meter drop. 45-meter drop. Doesn't the answer have to be this 30 meters per second? Let's see if it is. Oh, it is. Guys, what if the ball is dropped 125 meters? Should it have picked up to 50 meters per second? Let's try that one. So square root 2gh is, come on, 50. Oh yeah, sure is, sure is. Okay, see, same thing. They said. Okay. Oh, and finally, let me ask you guys a proportional type question. Suppose Bob and his friends are all throwing balls up the, nearby a multi-story building. Right? There's a bunch of windows. You say, hey, I could throw it up to the below-story window. Right? So we got like Alan and Bob and Carl and Derek and Eric. They're all throwing balls straight up. Right? Now Bob could throw up to, what was it, 45 meters. Suppose his friend Carl can throw 9 times as high. Guys, 9 times as high means he's really throwing how many times as fast? He'll be throwing faster. 3, right? Because I throw a factor of 9 on that h, right? That becomes also square rooted, it's underneath the root. That would be 3 times as fast, right? If you throw it 3 times as fast, you're throwing 9 times as high. Ooh, okay. And so you should throw it straight up. All right, you guys get there? All right, so here's a good little warm up. Tuesday morning warm up. All right, Kahoot time. You guys got, laptops out, ready to go. You guys are on. Flip over to Kahoot. All right, and start. One possible unit of speed there you go, all the above. All right, so, okay, miles per hour. Hey, that's what's on our car dashboards. Got that. Kilometers per hour. Do you think if you cross the border over to Canada, that's probably what they're using up there? Right? And look what the common thread is. Isn't it some kind of distance per time? Right? Let's check out this yellow one. Light years per century. Hey, a light year. A light year is like a distance. It's how far light goes in a year. And per century, what if you're zipping across the galaxy and you travel like 20 light years in 1 century? Hey, that could be a speed, couldn't it? Right? Yeah, all the above. All the above. Some kind of distance compared to time. All right, got points on the board. Points. Object moves 5 meters in the first second of travel, 5 meters in the next second, 5 meters in the third second. What is the acceleration of that object? Acceleration. Yeah, 0 meters per second squared. Right? Now, a different question could be, what's the velocity? The velocity is 5 meters per second, right? But it's a constant 5 meters per second, which means it's not speeding up or slowing down, which means there's no rate change of velocity. So acceleration is 0 meters per second squared, right? Guys, what if it was a rocket going like 5,000 meters, 5,000 meters, 5,000 meters, just screaming through space, 5,000 meters, 5,000 meters, 5,000 meters. What's the acceleration of that rocket? 0. Yeah. If you're inside that rocket, would you just feel like floating around? Yeah, just floating around. All right. If you were, in deep space, that would be true, right? All right, we got Zach, Lily, Alexander, Ziriana, Elise. An object falls freely in a vacuum. It's what increases? One winner. Velocity increases. Let's check this out. Okay. Let's look at an object falling freely. Hey, could that be, hey, drop a ball off a cliff, right? Drop a ball off a cliff. What's going on with, okay, so as time's ticking along, right? What's changing? Is the velocity increasing? Yeah, velocity is increasing, picking up 10, 20, 30, 40, 50 meters per second. it's picking up 10 meters per second every second, right? Which means that acceleration is constant. Is that constant? Yeah, acceleration is constant, isn't it? It's picking up 10 meters per second every second. That's a constant rate, right? So acceleration is constant and velocity would be increasing. All right, you guys good with why it's only velocity is increasing? All right, who got those points? Somebody. All right. So ball is thrown straight upward, is caught when it comes back down. In the absence of air resistance, its speed when caught is there you go. Yeah, the same as when you threw it. Right. Notice it says speed, so independent of direction. Right? One way it's going up, the other down, but the magnitude of velocity, which is the speed. Right, here's my classic example. I said you're gonna see this again. Right? Yeah, this won't be the last time either. Guys, this is a really handy page right here for today. So here's Bob throws the ball straight up at 30 meters per second. Right? Then it takes 1, 2, 3 seconds to hit the peak, then 1, 2, 3 seconds to fall back down. You guys see it slowing down on the way up and speeding up on the way down, right? But it's the same speed, right? Just opposite direction. Same speed, opposite direction. Right? Right. Let me ask you guys a little trickier question. Guys, if I said what's the difference in speed, you would just say 0, right? 30 minus 30 is 0. Here's a different question with a different answer. What is the difference in velocity from this point to this point? Notice the direction's changed. What is 30 minus negative 30?
Wait, what?
60. Yeah. It is a change of velocity of 60 meters per second, right? So yeah, and all those equations we've been using are really velocities put in. Yeah, just most of the time, if you can use speed and velocity somewhat interchangeably, but not all the time. That's an example. All right. That was a little tricky question. Here you go. All right, how are we doing? We got Lily, Olivia, Alexander, Zariana, Elise. Ball thrown upward rises and falls back to the floor. During this time, acceleration is always. Guys, which way does gravity pull? Downward. Let's look at this again. Right. So there's velocity, there's acceleration, two different concepts. So here's Bob throws the ball straight up. Now, the first 3 seconds, the velocity is upward. In the second 3 seconds, the velocity is downward. Right? That's velocity. But the question was acceleration. Right? Which gravity field is an acceleration? Look, guys, as soon as the ball leaves his hand, isn't gravity pulling down? Right? And then 1 second later, it's still pulling down, and then still pulling down. Yeah, gravity's always pulling down, and as long as the ball's in free fall, it's accelerating down at 10 meters per second squared. And that's true right up until the moment that he catches the ball. All right. So remember, velocity will tell you the direction it's moving. Acceleration is a rate change of velocity, which for free fall is just equal to the gravitational field. You got Zach, Alexander, Peyton, Zariana, Elise. Suppose you travel 300 kilometers, takes you 5 hours. What's your average speed? There you go, 60 kilometers per hour. There you go. All right, so you just divide it out, right? I went 300 kilometers, took me 5 hours, right? Now, the idea of average is, well, it's not true every second of the journey. Maybe sometimes you're going fast, sometimes you're at a red light, sometimes you're getting gasoline, right? So if you average it out. Here, I also want to say, these formulas we're using, guys, this initial velocity, this final velocity, are those average values? Or are those, if it's not average, it's what starts with an I? Instantaneous, right? Because the velocities you feed into these formulas are instantaneous values. We hardly ever talk about average velocity in here, but every once in a while. So there's an example of average velocity. All right, so you guys doing? We got Zariana, Olivia, Alexander, Elise, Peyton. A ball is thrown straight upward. At the top of the ball's path, its instantaneous speed is. Ah, you got 0 meters per second. That's good. We just solved that earlier today, didn't we? So, okay, if you throw something, goes maximum height. I know it's going 0 meters per second at the maximum height point. I could probably use that to help solve some stuff, right? All right. All right, we got Zach, Zariana, Alexander, Elise, Peyton on fire. The ball is thrown straight upward. At the top of its path, its acceleration is. Yeah, there you go, 10 meters per second squared. Here, you go back to this again. Take a look. Okay. Remember, the velocity is always changing. Sometimes the velocity is upward, sometimes velocity is downward. It's slowed down on the way up, it's speeding up on the way down. That's all velocities. But acceleration, guys, as soon as the ball leaves your hand, it's accelerating down at 10 meters per second squared, 10 meters per second squared, 10 down, 10 down, 10 down, 10 down, 10 down. Yeah, 10 meters per second squared, even at the very top, right? Where it's changing direction. There you go. All right, I got Lily, Alexander, Elise, Zach, Peyton. Car accelerates at 3 meters per second squared. How long does it take to pick up to 15 meters per second? Yeah, there you go, 5 seconds. So you guys could do 3 times 5 is 15. And just for completion, that's really this one right here, isn't it? So start from rest, this goes away. You got 3 times 5 is 15. Boom, 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 just like that. All right. Zoom in. All right, good. Freely falling object starts from rest. After falling for 5 seconds, its speed will be about. Yeah, it should be 50 meters per second. Let me point that out here. Okay, here's a drop off a cliff. It's been falling for 1, 2, 3, 4, 5 seconds. It's picked up to 10, 20, 30, 40, 50 meters per second, just like that. And the equation to back that up is, of course, this middle one again. Right, go 10 times 5 is 50. Starting from rest, this was 0. 10 times 5 is 50. There you go. All right. We got the pen number, Elise, Alexander, Zach, Peyton. When you look at the speedometer of a moving car, you see that cars. Yeah, instantaneous speed tells you how fast you're moving at that instant. Okay. Right, so if it says 30 miles an hour, you're going 30 miles an hour that instant. Right. Yeah, again, we hardly ever talk about average speed in this class, which would be like total distance over total time. But yeah, at instances. All right, we got John on fire, Zach, Elise, Alexander, Peyton. Car starts from rest. After 5 seconds, picks up to 30 meters per second. What's the acceleration? All right, you guys go 5 times 6 is 30. 5 times 6 is 30. As long as it... All right, lots of boards. Oh, yeah. In a vacuum, objects fall at constant. Yeah, constant acceleration. Constant acceleration. Here, let me point that out on this table again, too. Come on, switch over here. Okay. So here's an object in free fall. Object in free fall. Right. So time's ticking forward. Right. Hey, is acceleration constant all the way down? Yep. Is velocity constant? No, velocity is picking up. Now velocity is changing at a constant rate, but that's what acceleration is. Acceleration is the rate change of velocity. So velocity is 10, 20, 30, 40, 50 meters per second. It's picking up 10 meters per second, hence 10 meters per second squared. So acceleration is constant all the way down. And if you made a graph, that would look like a flat horizontal line, wouldn't it? Okay. Acceleration versus time. That's also constant. Acceleration. Right? Yeah, in this class, acceleration tends to be constant. Zach, John, Alexander, Elise, Peyton, on fire again. As drops of water fall from a leaky faucet, they one winner. One winner. Here, I'll show this to you guys. The answer to that question is also on this page. Because what if I have a faucet up here? It's go blip, 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 blip. And these are water droplets. You guys see these water droplets? Okay. So, hey, see how they're like spreading apart as they fall down, spreading apart? Okay. And the reason is that distance of time, there's a squared relationship. And the equation to back that up is this one right here. Right? So as time passes, they spread out more and more because you have to square the time to get proportional to the distance it's falling. Set. So here's my leaky faucet again. Blip, 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 blip. Here's a bunch of water droplets. They're spreading out. Bob can jump off the ground with twice the jumping speed of Alan. Just after his feet have left the floor. Yeah, Bob's downward acceleration will be equal to that of Alan's. Because remember, once your feet have left the floor, doesn't matter how fast you're moving or which direction you're moving. Doesn't the gravity field pull you down at the same rate? Right? In fact, you guys know what number that is. Guys, gravity field pulls you down how much exactly? 10 meters per second squared. Right? It doesn't matter how fast they jumped. It doesn't matter what their weights are. And then starting probably tomorrow, it doesn't even matter if they jump at a 45-degree angle. Yeah, gravity field is always pulling down at 10 meters per second squared. There you go. I got John, Alexander, Zach, Elise, Peyton. What is the value of G at Earth's surface? At 10 meters per second squared. There you go. There you go. All right. Everybody winning. Oh, yeah. And Lily in the top 5. Peyton still in the lead. Ball is dropped from the top of a cliff. Each second, its speed increases by about. Yeah, 10 meters per second, right? It picks up 10 meters per second every passing second. Right. Point that out. Okay, I missed that one. Okay. So it's saying from here to here is 10 meters per second. During the next second, picks up another 10, then another 10, another 10, another 10 meters per second. It's picking up 10 meters per second every passing second. I got Lily, Alexander, Zach on fire, Elise, Peyton. If you drop a feather and a coin in a vacuum chamber where there's no air drag, which will reach the ground first? Yeah, there you go. Able to tie. We back that up here. No. Ooh. Yeah, you guys see this bowling ball on this feather? It's in the world's largely down the same. Oh yeah, oh yeah. All right, let's get this back going. Boom. All right. All right, we'll talk about air drag in a few weeks, but we're not ready for air drag yet. All right, we got John, Lily, Zach, Elise, Peyton. Number 19, double points. A projectile is fired straight upward at 30 meters per second. The total time to return to the ground is it is 6 seconds. I'll show you guys 3 different ways you're going to know that. 3 different ways. Okay. One way is if you got this area notes, you could just count it. Couldn't you just count this frame by frame? Because here's 30 meters per second for the ball. You guys see 1, 2, 3, 4, 5, 6 seconds? Because 3 seconds up, 3 seconds down. Wouldn't that be true? Right? Or if you wanted to solve this with an equation, do you think you could solve it with an equation? Right? I'll show you guys 2 different ways to do that. Start with this middle one. Guys, if you throw the ball upward at 30 meters per second, how fast is it landing in your hand when you catch it later? 30 meters per second the opposite direction, right? And isn't gravity pulling at 10 meters per second squared the entire way, right? So that's going to look like this. Here, I'll show you guys notes from last class. So I threw it upwards at 30 meters per second. Gravity pulls down at, oh, whoops, sorry, this is plus here. Oops, okay, a plus. Okay. Gravity pulls down at negative 10 meters per second squared for some time so that I catch it at the same speed, opposite direction, right? Now, if I do the math, guys, what is negative 30 minus 30? Negative 60. Aha. Because on a number line, negative 30, 30, the difference would be 60 units, right? Then divide by negative 10. Hey, 6 seconds total. Again, 3 seconds up, 3 seconds down. So 6 seconds. That was the answer to the Kahoot, right? Or what if you do this? What if I play off this first one? Is if I throw the ball from ground level and it also lands at ground level. Guys, what is the displacement from the ground back to the ground? 0 meters. So let's try this one. What if I use the first kinematic expression, but I plug in 0 meters? Okay. So I threw the ball upward at 30 meters per second. Gravity's pulling down 10 meters per second squared. Now, time shows up in 2 places, but can I factor one of those t's out? So that's what I did from here to here. Just factor a t out. And then this bit right here. You guys see how I'm still going to get 6 seconds? Right. So yeah, there's 3 different ways to get to that answer. Can be, yeah, right. Right, you guys good? It's good. Oh yeah. Here, put this up here. All right, so we got 1 Kahoot question to go. We're going in for the win. We got, so share screen. All right. Alexander, Olivia, Elise, Zach, Peyton, who's gonna get some Kahoot medals for the win? Suppose a jumper claims a hang time of 6 seconds. That means you jump off the floor and you don't land on the floor until 6 seconds later, which would be crazy, but if that was true, you could jump how high? Little kid comes up to you, like in kindergarten. I can jump, and I don't land on the floor until 6 seconds later. Yeah, right, kid. But if that was true, you'd be jumping how high? Ooh, winners. 45 meters is what I'm looking for. Let me show you guys why it's 45 meters, then we'll see who wants some Kahoot medals. Okay. Guys, it's this scenario all over again. Because if you jump off the floor and land 6 seconds later, isn't that exactly this? Right? Takes 1, 2, 3 seconds up, 1, 2, 3 seconds back down. Is that right? If that's true, that means you had to have jumped at 30 meters per second. That would be true. And you're also landing at 30 meters per second, which would be probably wouldn't feel too good, but that's what would be, right? And then Ooh, isn't that true? That also goes hand in hand with all this math we've been doing since the beginning of class today. It goes 45 meters high, 45 meters, right? See if, oh, here can be. So displacement is v naught t plus 1/2 at squared. Okay? So I'm going to jump at 30 meters per second. Notice if you have 6 seconds total hang time, isn't that only 3 seconds to reach the peak? Right? And then plus 1/2 acceleration is pulling down at 10 meters per second squared. Here's 3 seconds again being squared. Right? So you run the numbers, you're going to get 45 meters. You guys see that? Right, this is another way to look at it. Right? Maybe here's another little bit way to look at it. Is if you have 6 seconds hang time, this might be the way I would think about it if I were back in high school, is you can split this problem in half. That means you're on the rise for how many seconds? 3. And that means you're also falling for how many seconds? 3. And then could you just go to the edge of a cliff and say, well, if you were falling for 1, 2, 3 seconds, how far would you have fallen? There's the answer again. I see 45 meters, right? And the equation that backs that up is, of course, this one here. We're talking about how much time, we want to know how far. That's definitely the first one, right? All right, so there's multiple perspectives of why. Okay. You guys right? All right, let's see who won Kahoot. Who won the Kahoot? And the podium with the bronze, Elise with the silver, Zach and the gold, Peyton. Runners up, Olivia and Alexander. All right, nice job, nice job. All right, so here, yeah, oh, perfect. Yeah, we just got a few minutes left in class. Here's what I do. Guys, here's your guys' take-home quiz. I'm gonna hand this to you guys right now. You guys write in your planner, take-home quiz, due Friday. You guys got any questions about anything? Got about 5 minutes to ask me.